Hello everyone. Welcome to the Construction Technology course. Today, we will learn about soils classification and engineering properties. It is hoped that, through this lesson, we can cultivate in you the craftsman spirit of loving science, continuous exploration, and innovative progress. First, let's review the content and characteristics of earthwork. The content of earthwork encompasses all processes involving the excavation, filling, and soil transportation, as well as preparatory and auxiliary tasks such as drainage, dewatering, and soil wall support. The common construction tasks in earthwork projects include, first and foremost, site grading, which involves the removal of obstacles, site clearance, determination of the design elevation, excavation and fill volume calculation, and proper earthwork balancing. The second common task is excavating trenches and foundation pits, which encompasses surveying and setting out construction drainage and dewatering, as well as earthwork slopes and support structures. The third task is earthwork backfilling and compaction, involving fill material selection, transportation, filling and compaction methods, and density testing. Next, let's examine the main characteristics of earthwork construction. Firstly, it involves large volumes of work and high labor intensity. Secondly, the construction conditions are complex. Thirdly, it is significantly influenced by site conditions. Based on the difficulty of excavation, soils can be classified into 8 categories: soft soil, medium soil, hard soil, gravelly hard soil, soft rock, medium hard rock, and very hard rock. Next, let's learn about the engineering properties of soil. The first engineering property is the water content of soil. Firstly, let's look at the concept of water content in soil. It is the percentage ratio of the mass of water in the soil to the mass of solid particles. The formula is W equals M subscript wet, means M subscript dry divided by M subscript y multiplied by 100%. It can also be expressed as W equals M subscript W divided by M subscriptus multiplied by 100%, where M subscript wet is the mass of the soil in its moist state. M subscript dry is the mass of the oven-dried soil. M subscript W is the mass of water within the soil, and M subscriptus refers to the mass of solid soil particles. It is important to emphasize that the water content of soil varies under the influence of climatic conditions, rainfall, snowfall, and groundwater, directly affecting the stability of earthwork slopes and the degree of compaction and fill projects. The second engineering property is the bulk density of soil, which refers to the mass per unit volume of soil in its natural state. It influences the soil's bearing capacity, earth pressure, and slope stability. The calculation formula is ρ equals m/v, where ρ represents the natural bulk density, m is the total mass of the soil, and v is the volume of the soil. Next, let's examine the concept of dry density. It refers to the mass of solid particles per unit volume of soil and serves as a key control parameter for evaluating soil compaction quality. It is calculated using the formula ρ subscript d equals m subscriptus/v, where ρ subscript d represents the dry density of the soil. M subscriptus is the mass of solid particles, and v is the volume of the soil. It should be noted that different types of soil have different maximum dry densities. For the same type of soil, its compaction degree varies under different conditions, such as variations in water content or compaction effort, resulting in different density levels. To a certain extent, The dry density of soil indicates the compactness of its particle packing. The higher the dry density of soil, the more compact the soil. The degree of soil compaction is primarily controlled by inspecting the dry density and water content of the filled soil. The third engineering property of soil is its looseness coefficient. This concept refers to the phenomenon that when natural soil is excavated, its volume increases due to loosening, and it cannot fully return to its original volume, even after vibration compaction. This property is known as the looseness of soil. The looseness of soil is represented by the looseness coefficient, expressed as K subscriptus equals V2 divided by V1, K subscriptus apostrophe equals V3 divided by V1, where V1 is the volume of soil in its natural state, V2 is the loosened volume after excavation, and V3 is the volume after backfilling and compaction. It is particularly important to note that the initial looseness coefficient, Ks, serves as a key parameter for calculating the volume of soil to be transported by vehicles and determining the capacity of excavation equipment. Meanwhile, the final looseness coefficient, Ks apostrophe, is primarily used to calculate the excavation volume required for backfilling. Next, let's explore the reference values for soil looseness coefficients through the following table. As clearly shown in the table, the initial and final looseness coefficients are provided for soil types 1 through 8. The fourth engineering property of soil is its permeability, which refers to the ability of soil to allow water to pass through. Soil permeability is represented by the permeability coefficient, K, which indicates the volume of water that can penetrate a soil layer per unit time and is typically measured in meters per day. This coefficient is influenced by factors such as soil particle size distribution and degree of compactness, and it serves as a key parameter in artificial groundwater lowering and the selection of various well point systems. You can refer to the following table for specific details. Finally, let's go over today's assignment. Through this exercise, everyone can check whether you have understood the key and challenging points covered in this lesson.